Question.
One more question. A small and short question.
Just a straightforward one.
Today I am attacked by big scholars, and that too alone on the stage.
The books of science are never closed,
Yes.
which means science is evolving. What we have today may not be sufficient to explain and even visualize and realize self, but who knows, tomorrow's science would be able to decode that secret. And therefore, we must keep this possibility of tomorrow's science decoding the secret of soul or secret of self open. This is what my suggestion is. Books of science are never closed. Every day science is evolving. We are getting better and better understanding of this vast creation. So I'm pretty sure mathematics may not be today, but mathematics of tomorrow may be able to comprehend and explain what we otherwise are not able to understand as reality today. Thank you.
It's a good comment by Professor Piyush Sharma. We should. It is a very intelligent and humble approach to be open. Sure, we should be open that tomorrow we may have answers. But and next level of humility, we should also know what we cannot know. This reality, we take it out of our pockets. Please do not take it out of your pockets. We should know what we cannot know. That's how the issues and foundations of physics and mathematics came in. Uncertainty principle is not a principle dependent on technology. After 1 million years, even if you have better technology, uncertainty is valid. The issue is, how come I have a limit in exploring the domain of nature? By H cross, Planck's constant, where, from where and how? I have no way to go further deeper. So there is this domain of knowledge that I cannot know is also, this is the gift of foundations of science. When we went deeper into science, into physics, into mathematics, it gave us black and white domain of which we cannot know. That is exactly, we are talking actually that in mathematics also this domain is there. You may get hints, you may get directions, but that domain is not accessible for you. That is the idea. Thank you very much.
Thank you so much, Sri Ravinagara.
Sure.
Thank you so much, sir. Now the next session will be given by on the subject Convergence in the Philosophy of Mathematics, and that talk will be given by Dr. Edward L. Zalta, Senior Research Scholar, Stanford University. So before we start, I'd like to speak some lines about him. Dr. Edward L. Zalta is a Senior Research Scholar at the Center for the Study of Language and Information. His research specialties include metaphysics and epistemology, philosophy of mathematics, philosophy of logic, and computational metaphysics. Dr. Zalta has published 2 books. One is Abstract Objects, an Introduction to Axiomatic Metaphysics, and the second one is Intentional Logic and the Metaphysics of Intentionality, as well as the articles in the Journal of Philosophy, Journal of Physiological Logic, Journal of Logic and Computation, Bulletin of Symbolic Logic, and among others. Dr. Zalta has taught courses and faculty seminars at Stanford University, Rice University, the University of Salzburg, University of Auckland, University of Tasmania, University of Padua, University of Santiago de Compostela, and Ludwig Maximilians University, München. Munich Center for Mathematical Philosophy, and has lectured in various universities in the United States, Canada, New Zealand, Australia, Great Britain, Germany, Australia, the Netherlands, France, Italy, Spain, Poland, Slovenia, Peru, Brazil, Israel, China, and Japan. His other physiological interests include modern logic, formal semantics, contemporary analytic physiology, contemporary history of philosophy and modern philosophy, etc. Dr. Zalta is also the principal editor of the Stanford Encyclopedia of Philosophy. So let's go on the talk over Convergence in the philosophy of mathematics, and enjoy. Thank you.
Thank you. Testing. You need me to test? Okay, we're good. Thank you. Well, thank you very much for that kind introduction. Today, and again, I'm very grateful for being invited to this conference. I'm going to try to give you a theory today of how to understand mathematical theories, no matter whether they're mathematical theories in the past, in the present, or in the future. I'll give you a formalism for trying to understand that, and that's how I will try to unify various philosophies in mathematics. Okay, so let me set up my question as follows. I'm going to suppose that logic provides a setting for mathematics, that without some principles of reasoning, mathematics is not possible. So logic is going to be in my background. But of course, some mathematicians, Boole and Frege and Church, give mathematical treatments of logic. But I'm not going to follow them in that regard. I'm not going to presuppose any mathematics. I'm going to follow Russell and Whitehead, who in Principia Mathematica from 1910 started with relations and predication and reduced sets and functions in terms of relations. So that's where my background is going to be. Now, to show you the power of that, let me note that the logicians suppose that an atomic statement has some logical form. X stands in relation R to Y. They write it this way with infix notation, or this way with the relation term at the beginning of the expression. And now they can unify not only ordinary language, language about two individuals, John loves Mary, but language about mythical characters like Jupiter. Caesar worshiped Jupiter, and 1 is less than 2, and 0 is a member of the unit set. I'm sorry, the null set is a member of the unit set of the null set. All of those 4 sentences have the same logical form. Right? So logic allows us to draw inferences in exactly the same way from all 4 sentences. So logic provides a kind of unified background framework that I'm going to presuppose for this talk. And in each of these cases, the names like John, Mary, Caesar, Jupiter, 1, 2, the null set, and the unit set of the null set, they denote individuals. Whereas these expressions, loves, worshipped, is less than, and is a member of, those denote relations. In this case, it's 2-place relations. But there can be 3-place relations, as you learn, X gives Y to Z, and there can be 1-place relations, which are just properties, like being happy, being prime, things of that kind. So logic is where my background starts. And then my question is, what do terms like 1 and 2 and the null set and the unit set of the null set, what do those terms denote? What things do we have to postulate in order to understand them? And my answer is going to be, they all denote abstract objects. And the thing to do as a metaphysician is to systematize the domain of abstract objects and show that the mathematical objects form one small subdomain of the domain of all the possible abstract objects. And that will unify various philosophies of mathematics. How is that going to happen? Well, the philosophy of mathematics is divided up into many different opinions. I'm going to show you now at least 8 or 9, possibly 10 opinions about what mathematics is. They try to give the answer to the question, What are those things that mathematicians talk about? There's the answer called Platonism. By Plato and Gödel, they thought that mathematics is in an independent reality that transcends nature. It's outside of the causal order. And Gödel believed in this form of this Platonism. Then there's the logicists. The logicists like Frege and Whitehead and Russell, they thought, well, mathematics is not something really independent. It's really reducible to just pure principles of logic, which we can know just by their meaning alone. And logical principles are supposed to be analytic and known a priori. And so they tried to reduce all of mathematics to logic. There's another, and that's very different from Platonism. And then there's another version of philosophy of mathematics called structuralism, which you get from, that goes back to Dedekind. Dedekind thought that there were all of these simply infinite systems of numbers, right? And he said their only properties were the other relational properties that they bear to this other members of this simply infinite system. And in recent times, that's been defended by Benaceref, Shapiro, and Resnick. Then there's something called inferentialism. Mathematics is not structures, it's simply the inferential role of the terms. We somehow objectify the inferential role. And that's something that Wittgenstein gave us, and Wilfrid Sellers and Robert Brandom. They all think that mathematical language is really just capturing, making explicit the inferential role of these terms, like the numeral one and the numeral and the membership relation. Then there's people who are like Hilary Putnam and Jeffrey Hellman, who think that, well, those simple atomic statements, 1 is less than 2, those aren't what's really mathematics is about. Mathematics is about conditionals of the form, if all the axioms of piano arithmetic are true, then 1 is less than 2. That's how you're supposed to interpret the statement 1 is less than 2, not as an atomic truth, but as the consequent of a conditional, the antecedent of which is the conjunction of all the axioms. That's very different from the ones that went on before. And then there's formalism. Hilbert and Curry, they think that mathematics is just a game played with formal symbols. And then there's naturalism, Quine. Quine thinks that the principles of set theory and mathematics generally are really part of natural science. They can be revised in principle, but they typically aren't revised because they stand at the core of our web of beliefs. And when we revise things because of recalcitrant data, we typically revise the physical theories before we revise the mathematics. But Quine says the principles of set theory are just like principles of physics. That's a little strange to me, but that is a position in the philosophy of mathematics. And then there's fictionalism. Fictionalism has been defended by Hartree Field and Goodman, which is also a kind of nominalism, which says those terms in mathematical theories, they don't denote anything really. Or if they denote fictions, whatever those are. And that's what fictionalism is. And finally, there's Carnapianism. Carnap thought that, any mathematical framework has about its own group of objects. And so he was very liberal in accepting all these different frameworks because he distinguished between do they exist as an external question and do they exist as an internal question. Internal to the theory, of course they exist. But external to the theory, he says the existence question is just a practical matter. So these are a lot of different philosophies of mathematics, and they're not compatible with one another, really. They don't look compatible. Now, I've left out some, and I may have left out your favorite ones, but I'll tell you why I've left them out. I've left out psychologism, because that's the theory that numbers and other mathematical objects are just ideas in the mind. I don't really like, I'm not going to talk about that because Frege had a devastating critique of that. And I've put aside intuitionism, constructivism, and finitism, not because they're not good theories. They're very, very good theories, but what they do is something different. They also advise and say to mathematicians, you should practice mathematics in a certain way. I don't want to tell the mathematicians how to practice. The intuitionists and the constructivists and the finitists say you should use only a certain set of tools, possibly a certain limited set of logical tools. I want to leave the mathematicians free to go to do whatever they want in developing mathematics. So I put those aside. Now, in the rest of my talk, I'm going to follow Stewardship Arrows' distinction between three kinds of foundational questions. There's metaphysical foundational questions, epistemological foundational questions, and mathematical foundational questions. I'm not going to be interested in mathematical foundations. That's for the mathematicians to decide. They may decide there's one mathematical theory to which every other mathematical theory could be reduced. It might be set theory, ZFC, plus some large cardinal axioms. It might be category theory. It might be homotopy type theory. That's a matter for the mathematicians to decide. And the reason is because once they decide, they may decide, yes, there is one foundational mathematical theory. My question then applies to that. What does the terms of that foundational mathematical theory mean? What do they refer to? And if the mathematician says there's no foundational theory, well, then my question applies to all the different mathematical theories. So in any case, I'm not going to be talking about mathematical foundations, only the metaphysical foundations and the questions about how can we know and get access to mathematical objects. So now, given that distinction, how do we decide among all those different alternatives that I gave you before? There's a problem that even confronts the people with all these different views, and some of them can't even agree on what the data is. Platonists think that 2 + 2 = 4 is just true, whereas the fictionalists say, oh no, that's false. That's like Pegasus has wings, or Zeus lives on Mount Olympus. Those aren't really true. They're only true in a story. Whereas Platonists say 2 + 2 = 4, that's just plainly true, not relative to any story. I'm going to show that there's two sides to this question, and that both of them are pointing to something that's right, but right now, most philosophers of mathematics can't explain why there's even disagreement about this question. So that's going to be an important thing. So we need an explanation as to why there are even divergent views about this data. And that's what a successful philosophy of mathematics should do. So now the final group of issues that I want to talk about is that if you look at the history of mathematics, starting, of axiomatic systems, going back to Euclid, the mathematicians have been using principles in the attempt to characterize entities whose only properties are the mathematical properties given by the principles. Now the problem is, with using modern logic, classical logic, there are no objects. There are no objects whose only properties are mathematical properties. Why? Well, because classical logic requires that for every object x and for every property f, either x has f or x doesn't have f. Or put it this way, where f bar is the negation of f, it requires that every object and every property is such that either x has f or x has its negation. Well, you might argue, let's revise classical logic, but I think there's a way of preserving classical logic, which makes a lot of sense to me, and that's what I'm going to be supposing. So I'm going to try to find a solution to this problem. How can there be objects whose only properties are their mathematical properties? Now, the logicians think that there's a formal solution to this problem. What they do is they formulate a mathematical theory in a language that's very restricted in its expressive power. So, for example, they formulate the piano number theory with just the symbol 0 and the successor function, the prime symbol, and then they say, so look, I've got objects and their only properties are the ones you can express in this language. But that's a kind of cheat. I mean, Russell saw through that already in criticizing Dedekind when he said, look, it's impossible that the ordinal should be, as Dedekind suggests, nothing but the terms of some relations as constitute a progression. Because if they're anything at all, they have to be intrinsically something. That is, they've got to be intrinsically, for every property, they've got to have either that property or its negation. Otherwise, they're not really objects. So, of course, one could revise number theory to include this predicate is a number, and 0 is a number is an axiom, and add that as an antecedent to all the axioms, but that's not a very successful story, because here's the question. Consider Zermelo's set theory. That's Z, that's this notion Z, Zermelo's set theory. Now you can formulate Frankel's replacement axiom. What happened? Good. You can formulate Frankel's replacement axiom in Z. But then the question is, in the theory Z, just Zermelo's axiom without replacement, you can ask the question, does the null set in Z denote a set such that replacement is true, or one such that replacement is false? Again, similarly, the continuum hypothesis is formulable in ZF. So does the null set symbol, that symbol there in ZF, denote a set such that the continuum hypothesis is true, or such that it's false? So there's a kind of mathematical incompleteness. Of course, mathematicians can't really define objects that are determinate with respect to every property whatsoever. And you might ask, how can there even be such completeness among mathematical objects? So what I'm going to then do is show you that there's a sense in which mathematical objects have properties in two different ways. Their internal properties are incomplete because they're just given by the theory, whereas their external properties like being abstract and not having a length and not being colored, I mean, the number 1 doesn't have a color, but that's not given by the axioms. So I'm going to argue that that's a property that is exemplified by mathematical theories. And so we'll be able to ask which properties of mathematical objects are the ones that they have necessarily. And we'll be able to address an additional worry to distinguish the numbers that Frege gave us from the numbers that Peano gave us. There are many different kinds of number theories. So that's how we're going to do it. The final issues concern the epistemological foundations. How do you refer and have knowledge of things that are not in space and time, right? We're finite beings, we have consciousness, but there's no light traveling from numbers to my brain. There's no information pathway from the numbers into my mind. So how is it that I can have knowledge and refer to objects, right? All of these philosophies of mathematics have this issue. The fictionalists and the nominalists think, well, I don't even believe in them as existing, so I get a free pass. But they don't. They don't really get a free pass. They have to give you an answer as to why it is that mathematicians think they have knowledge, mathematical knowledge. And so these epistemological problems are really serious problems for many of these other kinds of philosophies of mathematics. So I'm going to be operating under the following constraint, namely that a view of mathematics requires that we shouldn't postulate a transcendent reality that we can't access in order to get knowledge of those things. Because otherwise, mathematics will then just essentially be mysterious. I want to try to give an analysis of mathematics so that it becomes something that we know humans can engage in as a practice and do it successfully. Because if you think it's just a purely mystical thing that you can't access, then you wonder, why are we doing it so successfully, right? That's a problem. So I'm going to try to give answers to these epistemological questions that arise straightforwardly from the metaphysics. Okay. All right, now here's my quick outline, and then we're going to do something technical and give you a technical understanding of the solution. I'm going to produce a single logical formalism and use it to analyze arbitrary theories in mathematics. You'll see how. And then I'll show that this formalism has multiple philosophical interpretations. On one interpretation, it's Platonism. On another interpretation, it's logicism. On a third interpretation, it's structuralism or inferentialism. And you'll see that it captures, and I won't be able to go through the entire list in a short talk, but I will give you some idea of how that's going to work. So, and I will explain that there's disagreement about the data by giving a reading of mathematical statements on which every mathematical statement ends up having a true reading and a false reading. And that will explain why there's disagreement. And then the Platonists focus on the true reading, the fictionalists focus on the false reading.
And a false
And then
reading.
I'm going to try to
And that will
explain
why
the
there's
theory should
disagreement.
explain the sense in which the only properties that a mathematical focus on the true reading, the fictionalists focus on the false reading. And then I'm going to try to explain why the theory should explain
will emerge.
the sense in which the only properties that mathematical focus on the true reading, the fictionalists
Okay,
so now I'm going to give you the theoretical part. The theoretical part is technical, but it requires you, if you know already one course in logic, then the rest of this should be easy, because I'm going to add just one new technical notion in order to make all this work. I'm going to suggest that abstract objects, and you know, basically what I'm thinking of as abstract objects are things that are not in the natural world, but nevertheless we need to postulate them in order to characterize our states of consciousness. We need a kind of background theory that will allow us to say, this state of consciousness is about the null set, this state of consciousness is about the number one of piano number theory, this state of consciousness is about the continuum hypothesis in ZF set theory. So I'm going to suppose that abstract objects generally, they're not given in nature, but rather they're defined by the way we conceive of them. So it's our conceptions. You have a favorite abstract object? I ask you, well, what are its properties? You have to tell me what its properties are. That's your conception of the abstract object in question. And you're free to develop various kinds of abstract objects. Mathematicians are free, and they can say, I've got a relation that's transitive, symmetric, and dense as an ordering, and for example, then we might say that that's a mathematical theory. We might give him, he could give a theory of, let's say, dense linear orderings by giving you properties of a certain relation. And so that holds for every mathematical object that you can conceive of. You have a favorite mathematical object, you have to tell me what its properties are. I'm going to say that those properties that define it are encoded by that object internally, but they're not exemplified by that object. They're not exemplified as opposed to encode. And I'm going to use the notion of encoding to define these internal properties. Now, this notion of encoding comes actually